Zema, तो क्या अपना नाम भूल जाते हैं बार बार?
Okay, so
वो एक्सपोजर लॉक है ना असल में। ओए कसम से नहीं हुआ आवाज हाँ हो गई है।
so if we have a constant load, we would have a linear shear, we would have a parabolic bending. Yes. If we have a linear load, then we would have a parabolic shear and we would have a cubic bending. Okay, so that is something which you should appreciate. Now, in the case of concentrated loads, so if we have a concentrated load,
अब देखिए अब नहीं हिलेगा तो कम ज़्यादा फैट कम ज़्यादा करेंगे लाग तो वो होता है ना जब आपके पास इक्वेशन में एक वेरिएबल एक्स है ना कोई भी नहीं होगा तो स्ट्रेट एक्स आ जाएगा दूसरा एक्स स्क्वायर पे इसरा 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 और एक्स क्यूब पे
okay, in the case of concentrated load, what will happen? A concentrated load means that you have, as I said, load lumped at one point. Okay, so all your load is applied at one point. Now, the variation between the loads, so between these 2 points of interest, the variation between the load is what? What is the variation between the loads? No, that is 0. There is no variation. In case of concentrated load, there is no variation between the loads. Okay? The load gets constant. So there is no variation, yes? So if this is, so variation between the load, if that is 0, what will be your shear? Shear will be constant. And moment will be linear. So in other words,
ऐसे पूरा लंबी बनाएंगे ये चैनल होती है चैनल होती है किसी प्रोग्राम से इस तरह
so we have got a load applied over here.
Yes, sir.
We say that the clockwise normally is taken as positive. So if you take clockwise positive, it's up to you whether you take clockwise or anti-clockwise. Okay? However, but you have to then stick to that. So if the clockwise is positive, so what happens? Your shear is positive over here. Do you understand? Why? Because you will have load over here and the reaction over there. Okay, you will have reactions due to this. So if you take any point, you will have a shear applied over here, and that is positive. Okay, clockwise, if we say clockwise is positive, so this will become positive. Similarly, when you go to this side, what happens is that this load will be subtracted from this applied load P. As a result, your shear will be in the opposite direction, and that will become anti-clockwise. So this will become anti-clockwise over here, and see your shear, that's constant. Constant and constant. Okay? So that is constant, and that's what we mean that your shear is constant. Now, the shear will determine the slope of your moment diagram. So this slope will be determined by the shear, isn't it? What we established, the slope of the moment diagram can be determined from the magnitude of the shear. Okay, so if this magnitude is bigger, you will have a bigger slope over here. This is the slope. Okay, this is our slope, and this is our another slope. Do you understand my point? Yes. So this slope and this slope, that is a function of your shear. Your shear magnitude will give you the slope of these lines.
Yes, sir. That this moment will not close.
This moment now. No, this is just an arbitrary thing which I've drawn. Okay. So from using these tools, what we have established is we can draw the full moment, bending moment and shear force diagram. Yeah, that's what we can do. So now one thing is, so that is the first thing what we can understand from bending moment and shear force diagram. What's the other thing which it tells us? These diagrams. What's the other thing which these diagrams tell us? That is it doesn't give us deflection. It tells us whether our structure is in equilibrium or not. And how do we find that? If this gap is not getting closed, that means that structure is not in equilibrium. So if your shear diagram or your moment diagram, they are not getting closed at the end, that means there is something wrong, and your structure, your reactions and the applied load, they are not agreeing with each other. So this also tells us that is hidden, that's implicit in our shear force bending moment diagram. Okay, it also tells us, so first thing is, it tells us the variation of your shears and moments along the span. That's the first thing, that's the first information which the shear force and bending moment diagram gives us. And the second thing which is a bit hidden, and that is your equilibrium. It tells you whether your equilibrium is satisfied or not. So in other words, whether you have determined your reactions accurately or not. That's what also the shear force and bending moment gives you. Any question about this? Yeah, any question? Shall we rub it off then?
Yes.
This is the concentrated load. Shall we rub it off? uniformly distributed load. In the case of uniformly distributed load, which is like this one, the variation is, what is the variation? Constant. The variation between these 2 points is constant, isn't it? Yes. So let us do it again. So the variation is constant, which means to say that your shear is linear and your moment is parabolic. Okay, so this is linear and this is parabolic. Now, the same concept. You have got the applied load and that load is positive. Why? Because till the end you will have a positive shear, and we have said that in our sign convention is clockwise is positive. Okay, and we are drawing our moment on the tension side. Okay, so in our case we are taking tension side as positive. Okay, so you have the shear which is going linearly, it comes to 0 over here. Why? Because your reaction is equal to the applied load. So that's why it becomes 0. And then from there onwards, your force is in this direction. The force is down. So you have another force upward. So this is a counterclockwise direction shear. Do you understand my point? So in here, up till here, you have this reaction, this one. So in shear force, you always take all the forces which are from a reference point. In our case, the reference point is from the left. Okay, so from the left, we take all the sum of all the vertical forces. So this minus this, that is your shear force, and that will always be positive. Okay, so this will give you a positive shear force. And as you cross this point, what happens is your shear force becomes negative. Why? Because this half cancels out with your reaction, and then your positive force is acting down. So therefore you have a positive, you have got a clockwise in this direction, counterclockwise in that direction. And it is varying. Why? Because as you move forward, your shear force is changing. It's not constant. Previously, under the concentrated load, it was constant. Any question about this one? Now, in the case of, in this case, so that is your linear. Now, in order to draw the bending moment diagram, the bending moment diagram has got a slope. Where should it have the maximum slope? At the point where you have got maximum shear. And the maximum shear is at the end. So therefore, your slope is maximum at the end. And as we move towards the midspan, our shear magnitude is reducing. And so your slope is also getting reduced. See, this is the maximum. Maximum slope is almost 90 degrees, isn't it? and then you look at these tangents. These tangent slope is reducing as you move towards the midpoint. Is that
So if
okay?
we take tension positive, then the BMD will be in the positive x.
If you take it, yes, if you consider this one as a hogging moment, okay, so this is a as a sagging moment positive, then it will be on the top side, on the other side. But I'm considering it opposite. I'm considering my bending moment on the tension side.
So if we assume tension to be positive, like if we take tension positive, then will it also be on?
If you assume that tension is positive, no, I'm assuming that my tension is positive, but I'm saying that this is actually, this is my x and this is my y when I'm drawing it. My y is over here, that's what I'm assuming.
Figure you ulti ho.
Yes, that's what I'm assuming, that my y is in this direction, so that I get my bending moment
Sir, if we
on the
invert
tension.
the- if
Yeah,
we
you
invert
can do that. You can do that. The reason I'm more comfortable with this one is that, as I told you in the previous class, this tells me where the tension is occurring, and for me it becomes very easy to draw then the elastic curve.
Yes, sir.
Okay, and I can tell, like, I mean, where the reinforcement is required. Where, so that's why this is positive. That's why I consider this one. I consider it in this direction. So that is one thing. Now, any question about this? Any question? Any question? Come on, ask me if there is any question. Now, normally, when you are drawing your shear force and bending moment diagram for uniformly distributed load, especially in the frames, or if it's a beam where you have got lots of loads, you will always encounter a situation where you will be required to find out the point of zero shear. Isn't it? That's an important point. That's the important location where you should, which you should work out. Why? Because at point of zero shear, you have maximum moment. So you have. So how should we find that out? How can we work that out? So imagine. Let me give some values here. So I give. Imagine this is 25. Imagine, yeah, just random values. And this is the shear force. Okay? Now, how would I find out my zero shear? How can I find out this thing? Either similar triangle, or I find out the angle, the inclination of the slope of this line. If I find out the slope of this line, I can also, from there, I can easily find out my shear. So how can I do that? I can say that delta y by delta x is equal to, so 75 minus 25 is equal to how much? 2. Yeah, 75 is negative. 75 is negative, minus 25 divided by 25. This is minus 4 kip per feet. What is this? What is minus 4 kip per foot telling us? What is this? And also the applied load, isn't it? That is the applied load also. Is it not? The slope is equal to the applied load. That's what we worked out. So this is also the applied load. So even if you don't know, even if, my point is, even if you don't know, you don't want to go through this exercise, still you would know that this is 4. Why? Because you would know the magnitude of the load applied. Do you understand my point? Okay, so now if this is 4 kg per foot, how can we find this thing out? The area A1, this is A1, the area A1 is equal to half into 25 into, imagine this is B. This is B, 25 into B. What is 25? How would we find out RB? How would we find out RB? How can we find out RB? Can anyone tell me? How can we find out RB? How can we find out his B?
If you divide 5 by 4,
How much? Can I write 25 by B is equal to this slope?
6.25.
So I can write, and I can find out the area of this triangle.
Sir, can you please explain this point?
Look, I worked out the slope of this line. The slope of this line is -4. Okay. Now I have to find out what this B is. Yeah, that's my aim. So this B is equal to 25 by B. That must be equal to the same slope, isn't it? The slope is the same. We have found the slope, which is 4. So this must be, so from there we can find out the 6.25 and this
Sir,
6.25.
why didn't you put the negative sign?
No, but you can't have width be negative. That's why. I mean, like this negative is telling us that the load is applied in this direction. We have assumed load in that direction. So that's all it's telling us. So you have to use it a bit intelligently. Yes? Yes. So that's how you can find out what this centroid is, what this area is, everything can be found from this. So just by using, just through graphical, through graphical means you can work out these unknowns. Okay? Any question? Any question? Sorry?
Why would it be equal to slope?
Why this?
Why 25 by B is equal to the slope?
Because this is the same slope we worked out. What is this slope? Did we work out over here? Delta y by delta x. So this is the same slope. That's why it is. Yes.
डेल्टा वाई बटा डेल्टा मतलब पूरी उसकी है ठीक है पूरी लाइन